All right, welcome back. So we'll continue talking about magnetic forces today. So briefly, what we talked about last time. So magnetism is caused by, excuse me, it's caused by the current, basically. And for a magnet, it has two poles, a north pole or south pole, just like charges, like poles repel each other and opposite poles attract each other. The difference is for a magnet, you can cut it into small pieces, then each piece will have a new south pole and north pole. Um, so you can cut it down to even further ones, the smaller ones. Each of them will still have a south pole and north pole, unlike the charges. When you cut them into small pieces, no new charges will be generated. So fundamentally, as the current produces magnetic field, now current is produced by moving charges. So then if you have a moving charge in the presence of magnetic field, then it will interact with the magnetic field. So charge moving in the field will experience a magnetic force, F equal to the charge times the velocity times the magnetic field B sine of theta. This is an experimental result, and you can back calculate the magnetic field based on the force you measure. So in the vector form, the force, magnetic force is equal to Q, the charge, it could be positive, could be negative, times the velocity of that charge, cross product of the magnetic field, B. Okay, so F equal to Q cross B, QV, V cross B. And you can use the right-hand rule to determine what will be the direction of the magnetic field, magnetic force experienced by a positive charge. And for the negative charge, you will do the same, but at the end, you flip the direction of the force. So your four fingers lines in the direction of the velocity, and you curl them into towards the direction of the B field. Then the thumb points in the direction of magnetic force. Okay. We use magnetic field lines to represent magnetic field, just as we use electric field line to represent electric field. Motion of charged particles can be altered by either electric field or magnetic field. And the difference is for magnetic field, because magnetic force is V cross B. So that means force F is always perpendicular to V. So then it only changes the direction of velocity. But in this case, for the electric field, you will change the velocity's magnitude as well. If V and B are original not perpendicular to each other, then the result will be a helical path. In the previous case, V and B are perpendicular to each other, so then the motion of the charged particle is a uniform circular motion. All right, so we'll continue on today. So we'll talk about Hall's effect first. We'll move actually section 6 in front of 4 and 5 because section 6 is continuance of magnetic force experienced by charged particles. Okay, so the Hall effect, this is the result of if you have a conductor inside the circuit. Sometimes you might not necessarily have positive or negative charge as your charge carrier, like the most of the metal conductors, they have electrons as their charge carriers. In semiconductor or other types of conductor, you might have positive charge carriers, positive charge as charge carriers. Okay, so you can determine what will be the sign of the charge carrier, either positive charge carrier or negative charge carriers, by applying Hall's effect, so you will know the polarity of your battery or power source in the circuit, and then you have that conductor as part of the circuit. So as the current goes through here, if this is a positive charge carrier, then positive Q will move in this direction. Now you can apply external magnetic field, which is into the paper, in this case, the X here. So use your right hand rule, your forefinger in the direction of the velocity, and then you curl your forefingers towards the magnetic field. So then force is in up, point upward. So the charges will experience force in upward direction. So they will be deflected and then stay on the top here for the conductor. As a result, the bottom side of the conductor will have negatively charged on that side. So then you'll have actually electric field now produced. So the electric force is then in the opposite direction of the magnetic force, okay? So at a certain point, when you have enough positive charge accumulated on the upper plate here or upside of the conductor here, then electric force can be as big as the magnetic force. So then the charge particle here will no longer experience net force because magnetic force and electric force will cancel. So then it will just move straightforward. So you can put a voltmeter, which measures the electric potential across the top and bottom side of the conductor here, as this figure shows here. So in this case, this is the bottom, and this is the bottom side, and then this is the lower side of this. So if charges are no longer deflected onto this plate, then the voltage will no longer increase. Okay, so once you have the saturated voltage, then you know that this is no longer deflected. On the other hand, if you have negative charge carrier, so then again, right hand rule here, apply, let's apply one more time. 4 fingers in the direction of the velocity, and you curve it towards the B field. So you cannot do that. You have to flip it this way. So then you can curve it around. So B field is in the downward direction of F or B, magnetic force is in the downward, but this is a negative charge. So you have to flip it. So again, the magnetic force is pointing upward. So then that means negative charge will be deposited on the top side here, and then bottom side here will have positive charge. Okay. So the force, electric force, then will be pointing downward because negative charge will be attracted by positive charge down here. At when the magnetic force here upward matches up the electric force downward, then you have no longer accumulation of negative charges on the top plate or further accumulation of the charge on the top plate. So then this charge will go just straight through. So, and then at that point, you'll reach the saturation voltage, okay? But it will be negative in this case. So by telling the sign of the voltage, you can tell if it's a positive charge carrier or negative charge carrier. So then V of H is equal to electric field times the width of that, okay? So you can, and that will be equal to the velocity. So in this case, QE equal to QVB, okay? Just similar to the velocity selector, or E times E is equal to VB, or E times W is equal to VW, and then that gives the voltage capital V, okay? You can also use this to calculate the magnetic field if you don't know the magnetic field, but now if you know the other terms, the velocity and the electric field, etc. Okay. All right. So this is Hall effect. Now let's jump back to section 4 on the magnetic force on a charge carrying conductor. So if you have charge carrying conductor or the current carrying conductor, so that means there's current in the conductor, and it's placed into the presence of magnetic field. So then the conductor will experience magnetic force because each the conductor inside the conductor here, there's a bunch of charges that moves in the same direction that create current. So then on each of the charges, there will be a magnetic force, and collectively there will be an overall force on the conductor. Okay. So in that case, so just similar to the charged particle that in the magnetic field will experience a magnetic force. A current carrying wire or conductor will actually have a magnetic force on it. Okay, the magnitude of that force is equal to ILB sine theta. Okay, again, this is a experimental result. But in this case, because the magnitude is ILB sine theta, B is being a vector, so we can actually construct this as a new vector, either call it L, okay, a vector, or I as a vector. So then the result, so let's do the L here in this textbook. So then you can do I times L vector, which the direction of the L vector is in the direction of the current, and then the length of the conductor or the wire will be the L. Cross product B, because cross product gives you the magnitude of the two vectors times sine of the theta, the angle the two makes. Okay, so the angle theta is the direction of the current mixed with this B field, or this L vector makes with the B field. Okay, so I L cross B. Let's take a look on this example. It says the long thin wire shown in this figure is in a region of constant magnetic field. B, the wire carries a current of 6.2 and is oriented at an angle of 7.5 degrees to the direction of the magnetic field. Okay, so theta is 7.5. If the magnetic force exerted on this wire per meter is 0.038 newtons, what's the magnitude of the magnetic field? And if the angle changed, then as a result, the new force is 0.1016 Newton. What would be the angle, the new angle? Okay, so let's take a look on here. So we know that force equal to ILB sine of theta. Okay, so we can first calculate what will be the magnetic force by using ILB sine theta. Okay, F equal to, on this one, F equal to ILB sine theta, because we are only dealing with the magnitudes. Okay, so we can use this. For part A, we are looking for B field. So B then equals to F over IL sine theta. Okay, so you just plug in the numbers. I being 6.2 amps, L being 1 meters, 1.0 meters, sine of 7.5 degrees. So that gives you 0.047 Tesla of the magnetic field. Now B is asking you what will be the new angle. It gives you the F. All right, so F, and now it looks for, it's asking for the angle theta. So we can do sine of theta first. Sine theta equals then, according to this equation, F over ILB. Okay, so then theta equals sine inverse of F over ILB. Sine inverse of the force, 0.016 newtons, divided by the current, 6.2 amps, and L 1.0 meters. Now T 0.047. Okay. So this gives you angle theta as 3.1 degrees. That's the new angle. All right. Okay. So going back to the slide. So in general, the wire might not necessarily be straight, right? It could be curved up like this one shown in the figure. So in that case, then you'll divide the wires into small pieces of each one having a length of derivative of L, PL. So then the force on that small segment, derivative of force, that should be equal to IDL cross B. And you can integrate through, right, for the total force. So integrate through the wire to get the total force. Integration through the left-hand side equation gives you the net force, and the integration of the right-hand side equation, okay? So if that's the case. All right, next section here. So if you have a straight wire, then you can do L cross B. If you have a kind of loop, okay? So then, for example, let's start with the rectangular loop like this. If there's a current in the rectangular loop here, so then there'll be force on this guy on the top part of the loop and then the bottom part of the loop, okay? So these two have the same width or length, if you call it that way. Then force on this guy will be in one direction, force on this one will be in the other direction. So again, this could be done, direction of force could be done by using the right-hand rule. So your four fingers in the direction, or actually in this case, because there will be no force, I and B are in the same direction. So angle will be 0, okay? And then on this one will be also 0. Now, if in general, if it has an angle, but this one and this one then will be pointing in opposite direction. Okay, so they will kind of cancel out. But on these two sides, okay, in the figure shows here. So right hand rule says, so the current on this side will be going downward. So your four fingers will go point downward, and then the B field is in that direction. So the thumb is pointing towards you. Okay, so then direction of force will be pointing out of the paper, and this one then will be into the paper because the current is in the opposite direction. So in that case, one is pulling the loop in this direction, the other one is pulling it in that direction. So then there's a net torque produced if there's X rotation through the center of this guy. Okay, so what will be the net torque here? We'll calculate. So torque on the one side of the loop, right hand side of the loop will be ILB, right? And then so that will be the force times, so torque equal to force times distance, right? So ILB will be the force, or IHB in this case, L being H. Direction will be, or the distance will be half of the width, right? On the other side, it will be also IHB and then half of width. Okay, so this is torque on the other side. So they are both in the kind of in the same direction if you take it clockwise or counterclockwise in this case. If you have a top view here, then they are both clockwise. Okay, so they will add up. So half would cancel, add up to one. So IB, IHBW, but you can switch the position of H and W. So then H and B, switch H and B. So then IBHW. HW is the height times the width, though that will be the area. So torque then equal to IB, IB times A area, or IAB. Okay. So this is when you have initially the loop aligned with the plane of the magnetic field. Okay. Now, in general, your loop might be starting with a certain angle. Okay. So then the torque will be there will be a sign of the angle involved. So this angle is the angle between the magnetic field and the normal direction of the loop. Okay. So in general, torque equal to IAB sine of theta. Okay. So again, the direction will be normal direction of loop and then with the B field. So in the previous case, the normal direction of the loop, because loop and then the B field are in the same plane. So normal direction of loop will be perpendicular. So then will be sine of 90 will be 1. So then will be IAB. But in this case, it's IAB sine of theta. Now we get this result from a rectangular shape, but this would be true for any kind of shape or loop. It can be a square shape, maybe pentagon, or whatever, but or circular or whatever. Okay. So in general, torque equal to IAB sine of theta. Now, if you have n numbers of turns of loops stacking together, then you will multiply by n. Okay, so typically you have like n turns of coils stacking together. So n times of that, so you have more torque. Okay, so for if you guys look at the design of motors, then there will be multiple loops of coils stacking together. Okay, so NIAB sine of theta. So again, there's a sine of theta, and then I, okay, and then B there. So we can create a term called magnetic dipole moment, which is called mu with the arrow because its dipole is a vector. So that's equal to NIA in the normal direction. And B field is a vector. So then that's equal to this guy cross B field, okay? The dipole moment cross the B field. So this is similar to the electric field, the electric dipole. So torque by the electric dipole is P cross E. Now in this case, it's U cross B, okay? So dipole, torque for dipole is P cross E. We have U cross B as the U as the dipole moment. So for the potential energy, if in the case of the dipole in the electric field, we have minus P dot E. So then similarly, the potential energy for magnetic dipole in the magnetic field will be minus U dot B field. Okay, so this is based on that result. All right, let's take a look on example here. It says a circular coil or wire of radius 5.0 centimeter. Okay, so this is circular, radius is 5 centimeter, has 20 turns. So capital N is equal to 20. Carries a current I is equal to 2.0 ampere. The coil lies in a magnetic field of magnitude 0.50 T that is direct parallel to the plane of the coil. And it's asking you what's the magnetic dipole moment of the coil? What's the torque of the coil? Okay, so let's take a look on this one. So it says a circular coil, 20 turns, N equals to 20. Radius is 5 centimeter minus 2 meters. Okay. And so let's draw a circular coil. So magnetic field, let's say in this direction. Okay. So you could construct it either way. But let's say this is the X direction, Y direction, and then this is the Z direction, in the direction of the field. X, Y, and Z. Okay. The coil is in the YZ plane. Okay. So magnetic dipole, according to the definition, U equals to NIA in the normal direction of the coil. So the normal direction is in X direction. Okay, so let's call it that way, in I direction. So this guy is I, and it's 20. I think yeah, it says I equal to 2.08, 2.0 amps. The area, A is area, so pi r squared, pi times 5.0 times 10 to the minus 2 meters, and to be squared, okay? And then the normal direction, that is the I direction. So that would give you your magnetic dipole moment, 0.314 amperes times meter squared in the I direction, okay? It's your dipole moment. In part B, is asking you what's the torque on the coil. Okay, so the torque on the coil will be equal to the dipole moment cross product of the B field. So that will be 0.314 in I direction with the proper unit. So I'm going to ignore the unit for right now. Cross the B field. B field is telling you this is 0.50 Tesla, right? But that's in the K direction. So K direction. We can ignore the T because we are ignoring the units right now. So 0.314 times 0.5, that's 0.157. I cross K. So K cross I is J. So I cross K then is minus J. So minus of that J. Okay. The units will be newtons times meters for the torque. Okay. So this will be your answer for that. All right. So let's go back. This will be all the sections in chapter 11. So I think I will just stop here for today. So this will be a short lecture, but I'll come back next time for chapter 12. Okay, so see you guys. Bye.